it's the best way to understand it is basically a brand of big data geoscience. So most of its software and communication is done via GitHub. They set up cloud computing on Amazon and Google clouds to then work on these problems together. And it's mostly organized by people in the US, and Ryan Abernethy, a physical oceanographer from LDO, Columbia, but it's very inclusive. And they've been asking themselves this kind of question: what impacts the velocity of science? So how is the science workflow? And yeah, what determines the analysis velocity in a way? And here we are especially looking at the climate analysis point of view, not the writing of new modeling code or stuff. And so what determines this kind of speed, how quickly we can get along? It's data, software, and computation. And what I mean by that is, first of all, so data is the time to find, to access, to clean, to format for analysis, maybe even to download. Then the second part is which kind of software are you using? Is it like NCL, CDO, Python? Which kind of Python package? This part of the equation. And then the last one is computation. So this is mostly about access to resources and doing the computational time, what the CPU is doing. And now I want to start with a kind of provocative figure here about maybe the traditional analysis workflow. So lots of time, from my experience, goes into downloading or formatting or concatenating data, writing long scripts to actually get all the netcdf files together, to then, especially if it's a large data problem, to do some kind of batch processing, because yeah, it just computations don't go in seconds, but rather longer, or would even cause memory errors. And then the remaining time for the actual science actually gets rather limited. To be honest, that the DKRZ is downloading so much of the CMIP6 archive is actually a big time saver of this already, because one person or a few persons are actually doing the work, and a whole institute or everyone using Mistral can benefit this kind of communal effort in a way. Pangeo tries to reverse this kind of time allocation. They actually provide analysis-ready data in their cloud storages, and then they also have a pre-installed software suite, which is basically this Python thing, but you can also install your own software up there, with the idea that all these preparational things and data handling, copy pasting is heavily reduced in a way, and then also the computing is nicely parallelized, that scientists can spend much more time on the actual science. So the main message I want to deliver here is that from my point of view, all the data cleaning and data copying and copy pasting is not really science. It's just tedious manual work, which I think we shouldn't be doing more than we actually have to. And one way to reduce this kind of time could be intake. What is intake? With the primer taking the pain out of data access, it's a way to find and investigate and load data with catalogs. So when does intake make sense? It's mostly when otherwise you would be plugging together long scripts and paths of files repeatedly. And the basic idea is that one person is building a catalog in a YAML file once, and then you can use that that catalog to find data, even share that data sources easily with others. Those catalogs can be version controlled, and in a way, intake makes a distinction between the roles of a data curator and a data analyst. There's also caching implemented and some convenience functions. And the nicest thing about it is that it is open for plugins to also support other formats than the native ones. And we are now going to look into two of those use cases. The first use case is just imagine you have your modeling paper, and then a reviewer requests from you, well, you should somehow at least add some observations in there, and you don't really have an idea where to download the data from. How is the data structured in a way, or maybe you even know someone who has this kind of catalog with more than one data products available, and you just want to have a quick look into different implementations. And then intake-xarray could be a nice solution for you. As a disclaimer here, still all these things can also be done manually. You can go to a website, you can download a .NET file and open it as you would have done it before. But in the demo, I'll show you that once such a catalog is created, it can get much quicker and easier. So this is intake-xarray. Catalogs are pointing to basically netcdf file and group files, which are then, and intake is wrapping the xarray OpenMF dataset function. And as a short code snippet, you can see here two ways of accessing existing catalogs. The first one is about the ocean data on ICDC, which is also available here on Mistral. So Remon and me built together this catalog for ocean data, and you can access, I think it's 15 different data sets with this 3 lines, where in the third line you're just selecting from a list of data products that there are, and you get an xarray object when you're doing to dask. The nice thing about these catalogs is that you can also just share the location of the files, and it can be even remote climate data sets, for example, and even the catalog itself can be remote. So in the second example, I started putting together a few resources like head crude temperature, or the nice GIS temperature in a remote catalog where links are actually provided, and you can share that with a friend or with a co-author, and then the API is the same, but the data is then accessed locally on their laptop and even downloaded there or on Mistral. You'll see this in the live demo. So those are just 2 examples of catalogs, but you can also just browse GitHub and find other of those. Then the next, the second challenge is you want to do a multi-model SIMP6 analysis. And again, you can do all those things manually, but if you've tried to, you know how annoying it is to try to find which file has now been downloaded or not, especially if you try to do this in Bash. And then, yeah, what if a new model is available? Do you have to search again? How many ensemble members maybe have been downloaded? How to do the concatenation, the summarization version, if there is a new version, a file version available, and so on. And for all those use cases, if you're bothered about these questions or these bullet points, then probably intake-esm is something for you. So intake-esm has been developed at NCAR, and it's made to search and load a system model output. Those catalogs are built most easiest from summarized output, but you can also create those based on your own files, but it makes most sense to actually work on already summarized outputs, because the file naming is automatically identified. And in the end, you have a big pandas data frame, and in this you can query, you can have your search strings, and out of those you'll get your xarray stuff. And yeah, for example, you can here also share and archive which data sources you have been actually using for your particular analysis, or if you want to send, those are the 100 files that I use to a co-author, just to verify this is something. So now I will try to move over to the demoing part. I will share the other screen now. 1 second. No. This is the same screen again. And now. So I hope you can now see my screen. Florian is nodding. The rest of you is blackened out. Okay. Now I'm on actually a compute node on Mistral, and I just need to import intake. And we actually have a catalog for the CMIP6 data, which is downloaded by some group at DKRZ. Thank you very much for doing this. And Fabian Waxman has been writing a script that daily creates a catalog of all the files which are in this archive work IK 1070. And this is not the catalog file itself, but this is the rules how the concatenation of files then is working. And if we're here looking into this file, so this file everyone can access, and everyone should access actually to work with this intake-esm stuff. And here is the actual location of the catalog file. And then there is some attributes, which is not too important, but towards the end of the file, there is actually described how the aggregation of files is worked on. So every time there is more variables requested, they are all put together in one output. Also, if there is more netcdf files, only with the difference in their timing, they're concatenated together. And also the member IDs are getting concatenated together. So the nice part then is that to open a catalog is just this one-liner, open ESM data store. And here as a quick wrapper, we can see how many files are in this. And this is a super large data frame with 4 million paths, which are the 4 million files that actually have been downloaded. And there are many different institutions who are taking part in CMIP6, many different large types of experiments, like this is just the CMIP6 lingo here. Source ID is the name of the different models which are participating in any of these, and so on. And below this catalog, there's always a data frame, and a data frame is just a pandas data frame. And in there, here we can just see the first 5 files, where basically this long path, I'm not sure, is it large enough to read, Flo? Can you do some nodding or not? Because I think I can do some presentation mode.
Yep, that's good.
Maybe this gets a little bit larger. So we have a path here, and all the information is taken out of the path also. So which kind of experiment ID is it, which member ID, institution, and so on. And then the really powerful thing of intake-esm is that you can write a query. You can search that catalog, requesting all the files that have the experiment ID historical, table ID, atmospheric monthly output, just asking for the first ensemble member and the variable surface air temperature. And this basically brings us all the models to do the classic GMST plot. And if we do this, we now get here only historical AMON tasks. files. And well, some data cleaning sometimes is still needed. I think a few models just crash here. And then, yeah, we are extruding now 4 models, and then we only have 28 institutions. And now to get to actual xarray objects, we use this one function here, which is called toDatasets dict. So we want to have xarray datasets, and the output will be a dictionary, which you'll see later why. And here you can pass additional arguments to the xarray open dataset function. Yeah, here we can see at a list how this dataset names how the keys are. So it's a long list. We have also the MPI LR model in there, and I think also the HR somewhere. And if we now want to look in there, just taking a random one out there, we see that this is actually an xarray dataset. But if we are looking closely, we see that this is lazy data. So this is with dask. But we don't now want to process individual files, but rather all the ones in a go. But all these models are on different spatial grids. This is why it is not just outputted as one large data set, but rather this dictionary of data sets, because one model would have a curvilinear grid, another one would be somehow differently regridded, and so on. So what the next thing here will be that I will just be looping over this dataset dict and basically just extract a variable ID and do a spatial mean. So get spatial dimensions and then do the spatial mean just to be on the safe side, do a sort by time, and then add it to a list and concatenate it. And because this is all dask, this goes very fast. And the end result is this data array in which we are having all the models with our monthly output, but no spatial dimensions, already a mean, but we have only created a task graph so far. So all the computation we still need to do. This is just the concept of dask, but we'll be collapsing 11 gigabyte to less than a megabyte. And now for the fancy visualization part, for dask, you can also load a client and look at the dashboard and see how the computation is done. So we'll also do this here. We see that we are on compute. The dashboard is over there. So this is now, for some people, it's maybe interesting for debugging. It looks impressive, but it takes a bit of a while to read out very useful information out of this. But here, before this DA is still this lazy data. And when we compute it, we actually have the data in a way in memory to work with it without having to recompute it every time, basically. And if we do this, the whole analysis is triggered. So before we've just said the computer, this is what you should be doing. And now we see here on the side, like all the gray part here is not yet computed. We're waiting for this. And the blue part is already computed. And up here we see mostly it's the open data set and concatenation operation that is being done, because this is what we are doing. I didn't do any science yet, what I would say. But the nice part is here that this is running distributed, although I didn't really say anything about how to parallelize the whole thing. This is just the underlying dask and philosophy. So this now takes, a minute. So the whole thing to get to this point where you have everything in this format an array of model and time dimension. Takes maybe 5 to 10 minutes. And then from my point of view, the science part starts. Maybe as a small excursion, I could also, so now I'm computing, doing all the computation also on that compute node that I've been on. I could also start via Slurm and just dask job queue. I could request multiple nodes and do the same thing on more resources. And I did this once and I got the computation only in 30 seconds run, whereas here, when it will be soon completed, we'll see that it's like 2 minutes or 3 minutes. So my philosophy here is, as long as I can collapse the data onto something smaller than a few hundred megabytes, it is useful to just call compute, because then the eager computation makes more sense than doing everything in dask. Okay, just looking into the questions. Do we have questions? I don't see questions yet. Okay, here this now. So now we have this result, DAC, and this is really an actual number array that we are seeing below. So it's not lazy data anymore. So this is basically, I don't need this anymore. Now I want to do this multi-model plot for GMST. I do my year mean operator. And now in this line here, I'm loading data via intake-xarray. I'll explain this later in more detail, but basically I'm reading in a catalog, extracting the hat crude file, and doing in the same way my spatial mean. Then I'm appending this also to my all models file, because then all the science I would be doing it the same way on the model and on the observations. And then basically, yeah, my goal is to do an anomaly GMST plot. And from my point of view, the only point where I do the science is then actually this line, where I say this file where all my data is in, I want to plot not GMST, but GMST anomalies with respect to the 60s to the 90s. So do an anomaly with respect to that time and then do a year mean. This is already where, from my point of view, the science in this part has ended, where probably you want to do more stuff with then. But this just as a demo. So I would just for plotting purposes, drop the observations and plot it then in a different color again. But in a way, those lines can be enough to do this plot. Okay, so this was intake-esm, where you can basically do this query and search that I've been showing up here. You can do for whatever fits your research needs best. Here you can plug in a different table ID, different experiments. You can also check out this require all on thing. There's a nice documentation about it, but if you need a weird combination of files, which is very annoying to find by hand, there's a few nice convenience functions in intake-xarray. As a second thing, I wanted to show this observations intake-xarray thing. First, the ICDC catalog. This is how it is loaded, and currently we only have ocean data. And Remon didn't get much feedback, honestly, on this. So if you're interested in this, let him and let me know about it, because he especially doesn't want to create another of these catalogs for the void. So he would do something like this if it is used and if he gets feedback on this. But yeah, so if you are interested to get the atmosphere part or the reanalysis part, however ICDC is structured, please let him also know. here I'm demoing a bit how the ocean part is working. So a quick way to look into which datasets are available on intake-xarray is just to get a list view of the catalog, and those are the ones that Remon has implemented. And how to build a catalog, it's not dark magic. Here we can look at one of those YAML files. So first you specify a bit internally for intake, but then you're adding just a source. You give it a name, then you can give it a description, a driver name. Metadata is optional. And then the important part is actually this URL path. And this is what goes into Xarray open dataset. And then additionally, and also this is sometimes useful, to give additional keyword arguments. So decode times when it's a weird time that would break intake-xarray, or to drop a few variables that might also break with open dataset. And then there is more. And the way to access these is basically just this to dask, and by to dask it means to Xarray, but it's usually loading with lazy data, and then you can just select a few levels, like work on as you would do in Xarray. Here doing it a quick plot. Another thing I want to show is remote, or the possibility to have also remote catalogs. So here again, import intake. If I would have internet access on Mistral on this compute node, I would be running this line here, which is loading the same file which I downloaded here. So everyone in the internet could do this if they have intake-xarray installed. And here we can have a quick look how this looks like. So for a remote source, we here give it again a name. Metadata is nice, but we'll come to that later. And here I'm giving it just a URL path, which is really a remote path like this. If you click on this, it would be linking directly to the netcdf file. And so this is a way you could share with a co-author. Those are the few, the 5 observational products that I've been working with. They're all in this catalog. This is how here you can use it, or you can use it on Mistral or on your laptop in the same way, using the same catalog. With this simple cache key in front of it, it would also download it to your local file, that you don't have to recalculate, re-download it every time. This is just a really nice gimmick. And so what I've been doing before is I've opened in this atmosphere catalog. You can also do catalogs of catalogs, a catalog of catalogs. This is what I've been doing before for the plot, and this is exactly what we have seen in the plot now, just without the models. Another, again, playing around stuff with intake is you can also predefine plots. You can, on the one hand, for this you need to install hvplot, and in this YAML file up there, I defined actually a plot, or 2 different kinds of plots: a temperature anomaly over time, where you can, there is a syntax how this works, which is living on hvplot. And this is actually a way to send maybe to a colleague just a plot. So we have these 2 plots here. And in this one, you could just specify at which time series you want to look at. I'm not sure whether this is too useful. Or also here to have, it's not like NCView, but it's towards this direction maybe. to browse through it. The main idea is you may not need to know much about the data itself. If someone has predefined a plot, you can just use it and play around with it without understanding too much in the first place. In the end, I would still encourage you to really try to find out which is the data, because you want to understand this. And then here this shows how the caching is possible. That here in this case, in that folder that I'm working in right now, I downloaded the headcode data actually to disk, which I did before the session because now I don't have internet access. And with this, I come to the end of the live demo. And I just have, I think, one more slide. Oh, I don't want this way. Swap it. Yes. Okay, so how does actually Pangeo do it? They actually downloaded all the, they also have their CMIP6 replica, but they put all their replica into the cloud, onto a Google and Amazon cloud. And then they also have the possibility to get compute nodes basically sitting right next to the data, also on the cloud, so real server-side computing as I understand it. And you basically have an interface like jupyterhub.dkrz. They have something like this for the Pangeo cloud, where you can get access if you write an email to Ryan. And they even did put all the reproducibility thing one step further. They have a Pangeo gallery where you can actually do all your science in a GitHub repo. So they have the cloud in the data in the cloud. They have the computational resources which are available, and you can put also your analysis code in that GitHub repo, link it to Binder, and then ideally maybe even make your whole analysis code and make even a reviewer or some PhD student afterwards redo your analysis code. There's also, when you, I think, download the slides, you can also click on a binder that I created for different purposes, but they also have access and a few snippets about the CMIP6 data in the Pangeo cloud. And this brings me to now my conclusions. So my informal conclusions are: be lazy and use what is out there on the one hand and contribute to make that better. And the formal conclusions would be: use intake-xarray. For me, it helped a lot, made my life a lot easier in a few instances, namely intake-xarray for observations, something like ICDC or even a remote catalog, and intake-esm for summarized ESM output. I'm looking forward to questions and comments now. Thank you very much for listening.
Thanks, Aaron. So we actually have a few questions. The first one, I put maybe just say a few words about lazy and eager data, because I think not everybody's used to it.
Yeah, so, oh no, I see the questions. So I think the way everyone knows, like eager data is data which is in memory, which is the way you're working with. You've been working with NumPy or also with CDO. So data is in memory, and then you do computation on it. And with the lazy data, the idea is that you first only load the metadata and the coordinates, but not the actual values itself, and build a task graph, which is then later on executed and often also in a parallelized way